so it's going to change to concave down. So you have to, so it's asking you where is it concave up and where is it concave down. You see that blue dot that's labeled on there? Does everybody see that blue dot?
Yeah.
That blue dot is called what type of point? It's a point of what?
Inflection.
It's a point of inflection. A point of inflection is where the graph changes what?
Changes concave.
Exactly. It's where the graph changes concavity. So at that point it changes. So you have to estimate. So I'll make this a little louder here. This point right here, you have to estimate what that value is right there, and it's the x value. So like what x value is that right there? So what did this answer key estimate it to be? Negative 3/4 right there. So it's going to be concave up from negative infinity to 0.75, and then it's going to be concave down from negative 0.75 to infinity.
Oh, so it has to do with all of
Concavity. Second derivative is concavity. Second derivative tells you all about concavity, yes. Positive, it's decreasing when the derivative is negative. It's concave up when the second derivative is positive, and it's concave down when the second derivative is negative. So for the first two, you need the derivative. Here's the derivative. So it's asking where is 3x squared greater than 0? Where is that greater than 0? Everywhere except for what? Everywhere except for 0. Everywhere except for 0 is this one right here. Why is it not super accurate to say this? Because that includes what?
0.
That includes 0. That technically speaking, at x equals 0, is the graph falling or rising?
No.
Neither. It's at that one particular instant, it's not going up or down. So then you're asking, where is it negative? Is it negative anywhere? No. X squared is always positive. 3 times a positive number is always positive. So is it ever decreasing? No. And if you think about what does x cubed look like? It looks like this s, right? Is that ever decreasing? Okay, and then second derivative. What is the the second derivative is 6x. Where is 6x greater than 0?
From 0 to
Infinity. And then where is it less than 0? From negative infinity to 0. Look at the graph again. Where is it concave up? It's concave up from 0 going, oh, that's the wrong color, right? What color did I use? I think I used green, right? So if that's the graph of x cubed, concave up is right here, 0 to the right. And where is it concave down? To the left of 0. So does that match the algebra down here? Yeah, where is it less than 0? It's less than 0 when x is less than 0. Cool, yes?
This is just a
So we're going to go down to second derivatives. Nice, okay. So if I give you a derivative, there's a lot you can do. There's a lot you can do. So let's talk about this first thing. This first question asks, find the x coordinate of each maximum. Show me with your hand where a maximum could occur on a graph. Show me with your hand, like moving your hand around. Where could a maximum occur? The 0, and you're solving for me. So it's just x squared plus x minus 6 equals 0. Solve that for me. So when you have that, factors into what? You can tell me. X minus what?
minus 2,
Mm-hmm.
x plus 3.
So we know that x is going to be equal to 2 or negative 3. So we're interested, where's the derivative positive, where is it negative? So we had these number lines. So you make your number line, you label negative 3 and you label 2. This is the x value and this is the f prime value. So what's the f prime value at each of these? 0, right? Is it 0 anywhere else? Is the derivative 0 anywhere else other than these two? No, if your algebra is correct, these are not only answers, they are the only answers. There aren't any extra answers out there. So what does it mean about the values of the derivative? There's 3 regions here. There's this blue region. Let's call this a green region right here. And then let's say the yellow region. What's the only thing you can tell me right now about each of these regions? What do you know definitively about these regions? They're entirely what or what? Positive or negative. Why do you know they have to be, and this is very important, why do they entirely have to be positive or negative? Why can't the blue region be positive and negative?
because it doesn't cross 6.
So if it was positive and negative, it would have to cross it somewhere. It would have to be 0. Are there any other zeros? No, there aren't. So this is entirely positive or negative. This is entirely positive or negative. This is entirely positive or negative. How do you figure out pretty quickly if this is positive or negative? What do you do?
Plug in a value.
Plug in a value. Now what value is nice in between here?
0.
0. You can plug, you can plug in 1, that's fine. Plug in anything you want, but plug in 0 into the derivative. Plug in 0 into this, what do you get?
-6.
So what is that region, what sign is that region going to be? That region's going to be negative. Now, do not assume the other ones are negative or positive based on what you just got. You have to test numbers. So we tested 0. What's immediately to the right of 2?
3.
And what's immediately to the left of negative 3? Negative 4. So you could plug those numbers into this right here. This is the function value. This is the function value. So if we plug in 3, what do you get? If you plug in 3, what do you get? Positive or negative? You get 9 plus 3 is 12. 12 minus 6 is what? 12 minus, yeah, positive. What about negative 4? What do you think about negative 4? Are you guaranteed to have it switch at each point? Is it always going to go plus, minus, plus?
No.
Could it go minus, minus, minus? Absolutely. Like on x cubed, the derivative is always positive, right? It's rising, it gets to 0, and then it's rising again. So it's plus, 0, plus. That right there is not a max or a min. Yes?
When you say the max happens at x cubed.
Because what's going on right here? The function is it increasing or decreasing? The derivative is positive, so the function is increasing. And then what happens?
And then it goes negative.
So we know this is, now the big, I think what you're getting at is, I might have given you this word, this is a local max. That's not a word that you're going to see yet, but I'll give it to you right now anyway. So all we know, Nick, all this sine graph tells us, everybody, by the way, this is called a sine graph. Connor, hold on. All we know is what's going on. It's increasing to 0, and then it goes down, and then it goes back up. So up until this, there's x equals negative 3, and this right here is x equals what? 2. We know that what's going on here, it's decreasing from here to here, but what's going on to the left of it, what is it doing? It's increasing, and what's it going on to the right? It's increasing over here. So what can we say what kind of point is this point? This is the top of a mountain. This is the bottom of a valley, right? But here's the thing. This graph continues here. Are they absolute maximums?
No.
Why aren't they absolute maximums? Well, where's the absolute maximum?
Infinity.
It's way up here, right? But in this neighborhood, is this a maximum?
Yeah.
In this neighborhood, is this a minimum? You're going to spend a lot of your time in calculus finding maximum and minimums because they are very, very useful points in many ways. If you have a function that models like profits versus cost, you want to know like how much you're charging for an item, how much you make. It might look like this and come back down. So if you want to maximize profits, you're looking for the highest point. You're going to do this simple mechanism over and over again. You're going to have a function, you're going to take the derivative, and you're going to set it equal to 0. You're going to do that a ton. If you're ever totally lost on a calculus problem and you literally have no idea what to do and you have time, like there's no other problems to work on, I'm being totally serious here. Take the derivative of the function, set it equal to 0, and see if that helps you in any way. You're going to do that literally, not the new teenage definition of literally, the actual definition of literally hundreds and hundreds of times in this class. So, one big question though, are those points? Is x equals negative 3 a point? Is this a point? Neither one of those are points, they're just x values, right? So I might ask you, you don't do it, just you're going to answer this question for me. If you wanted to find the y value, what do you traditionally do? You take the
Function.
you take the function, you take the x value, and what do you do? Plug it in. Here's the thing, do we have the function? No, what do we have?
The derivative.
The derivative. We don't have the function. We don't have the function, and there's something really important for you to realize at this point. This is super important. If I said, here's the function x squared, and I said differentiate it. What is the only derivative of x squared? 2x. Let's say I gave you x squared plus 7. I said, what's the derivative of x squared plus 7? 2x. If I said x squared plus, I don't know, pi, what's the derivative? Okay, so you can take derivatives and get the same thing, right? So if I asked you this, the derivative of what is 2x? How many answers to that question are there?
Infinity.
There's an infinity of them, right? So here's the thing. Do we have any idea exactly what this other function is? No, there's an infinite number of choices because what number can you tag on right here? You can tag on any constant you want. You can tag on any constant you want. So if I asked you what's the y value, you would say, I can't determine that. I need more information. Okay, so let's talk about this derivative here. We have the derivative. Say we still have this derivative. If I ask you for the points of inflection, what does an inflection point mean? It's where what happens?
Concavity changes.
Concavity changes. That's really important. So if I ask you for the definition of inflection point, you would say it's where concavity changes. That's the definition I want, where it changes. So if that's the first derivative, what derivative do we need to look at to examine the points of inflection, to find them? The second derivative. So what's the second derivative now? F double prime of x is going to be what?
2x.
Plus 1. And what do we do with that function? We set it equal to? Set it equal to what? 0. So we get 2x is equal to negative 1. So what does x equal? So you make a number line again, and you have negative 1/2. And this time it's x, and this is the second derivative value. So are there any other places where the second derivative is 0? Nope, there aren't. So to the right, it has to be all positive or negative, and to the left, it has to be all positive or negative. So what value do you want to test on the right? What's an easy value over here? How about 0, right? How about the negative 1? Well, plug in 0 there, what do you get?
1.
So it's going to be positive here. And what about to the left? If you plug in negative 1, what do you get? Negative. So this function, actually, that should make sense to you, because what does 2x plus 1 look like, everybody? Where's that cross the y-axis? Crosses at 1, and the slope is 2, so this is 1/2 right there. So what do we know is happening over here? This value right here is positive right here, because it's above the x-axis, and it's negative below it. So if the second derivative is positive, what does that tell you about concavity?
Tells you that the point of inflection is negative 1/2.
Yeah, so change in concavity at what? X equals negative 1/2, right? So we know, what does second derivative positive mean? What does that tell you about the concavity? It's concave what? Concave up, and this one means concave down. Absolutely. Fantastic. It's super exciting. I know, you're just thrilled about this. Most people found, they said, I like this. X equals negative 2/3 is where the first derivative is 0, and so is 2. And what you could say in complete sentence form would be, there is a, I like this word, local, if you want to put that in, local maximum at x equals negative 2/3 because the function is what to the left?
Positive.
The function is rising,
Right.
rising to the left, and what? To the right. There's your justification, and falling.
Gee whiz.
I don't understand that second part. The rising to the left and falling to the
Yes, so at x equals negative 2/3 right here, we know at this point, what's to the left? You know the function is rising because the derivative is positive, and you know it's falling. So the function is rising and then falling, so what has to happen here? A maximum.
yeah.
That's what it is. Sorry, you have to hit C. Nice. Okay, so then what do you say for x equals 2? There is a what? Local minimum at x equals 2, because to the left of x equals 2, the graph is falling, and then to the right it's rising. That would be a great, takes 10 seconds to write that. 10 seconds. How do you find the points of inflection? What function do you need to examine to find points of inflection? The second derivative, right. So the original function was, what was the original function? What is it? X cubed plus what? X cubed minus 2x squared minus 4x plus 8. So what's the first derivative? You guys did this already. It was 3x squared minus what? 4x minus 4. So what's the second derivative? What's the second derivative? 6x minus 4. You want to know where does concavity change. So you want to know where the second derivative goes from positive to negative. So you set this equal to what?
0.
So you know that x is going to end up being 4 over 6, which is 2/3. That's not enough. You need to check both sides. You need to check both sides. So you do your number line here, and you have 2/3. That's your x value, and this is your second derivative. You know, at 0, you need to test values to the right and to the left. What's to the right of 2/3?
1.
How about 1, and what's to the left? 0. And you're plugging it in here. Plug in 1, you end up with a positive number, and plug in 0, you end up with a negative number. So does concavity change at x equals 2/3? Yes. At this point, all of you would have gotten about 8 out of 10 points if you had done all of this that's on the board, because there's something that's missing from each of the points. Oh wait, what is the same parenthesis at A? Points. Are these points? Are they points?
No.
Why couldn't we find the points before? Because we only had the derivative. Do we have more than the derivative this time? What do we have? What's the first line? We have f of x. What could you do with all of these values? You could take these values using your calculator, plug them in, because it'd be a little, it's not that bad, but it's not that nice either. Could you find the y values?
Yeah.
Yeah, you could find the y values.